Okay, hello everybody. Hi. I'd like to welcome you all to our talk today by Emily Wall. She's visiting us from Georgia Tech, where she's completing her PhD with Alexander. And she's working at the intersection of data visualization and cognitive bias. It's a really exciting topic that actually also has had a lot of successes in her research career. So for example, one of her systems was integrated and has now transformed into a Microsoft product group. She's also won a number of fellowships, and I'm really excited that we have her here today. I would briefly like to point out that it's totally fine to ask any clarifying questions during the talk, but please keep any longer questions to the end of the talk so that we can actually hear the beginning and the end of her talk. And otherwise, please join me in welcoming Emily Wall.
Thank you for the introduction. Is volume good? Can everybody hear me okay? Cool. So today I'm talking about work that I've done toward detecting and mitigating human biases in visual analytics. So the title of my talk began with "As We Are," and that's a reference to this quote by Anais Nin that says, "We don't see things as they are, we see them as we are." So perception of the world isn't objective, right? People are biased in all sorts of ways, and that influences the way that we see the world and the way that we interact within it. And sometimes those biases can have some heavy consequences. So for example, in 2004, there was a series of train bombings in Madrid. The wrong man was charged and imprisoned because there were fingerprint analysts who were subject to confirmation bias. So there was a partial fingerprint that narrowed down the search of those suspects to a few dozen people. And among those was Brandon Mayfield. So he was an American man. He was a lawyer. And he had recently represented a man with ties to a terrorist organization. And he had also recently converted to Islam. So the FBI ultimately arrested and built a case against an innocent man due to this bias. So if we have the power to help prevent errors like these, then we can have a really big impact. So the question then is, what does this have to do with visual analytics, right? So in visual analytics, we advocate for the combination of humans and machines. And we think that we can really get the best of both worlds, where we get computers giving us fast and accurate information processing, and humans give us sense-making capabilities and domain expertise. And helping people make these data-driven decisions can be really vital in a variety of domains. So, for example, choosing a healthcare provider or a treatment plan based off of data from clinical trials, or helping make consumer purchasing decisions. So what products are you going to trust, or what car are you going to buy based off of reliability ratings? Informing policymakers to understand how public opinion in certain regions might be affected by particular policies. And understanding potential security risks. And the point is that when situations are critical, we ultimately rely on people to make those decisions. So in the Viz community, we've addressed those kinds of questions for years by building systems that look like this, where we combine analytics and computations with the power of human perception. So what we haven't really considered until recently, though, is what limitations humans might be bringing into this analysis process. So for example, like confirmation bias that I mentioned earlier. And the key to understanding those limitations in my research comes to us courtesy of the fact that we're using systems like these more and more to analyze data and make decisions. And the way that people are interacting with that data gives us some trace of what a person is thinking, their reasoning processes, and the biases that may be informing that process. So the interactions are a form of data about the person who's performing those interactions. So there's an abundance of work making inferences about a person from their interactions. So for example, some work has leveraged user interactions to steer analytical models. So for example, if you have a bunch of dots representing different documents, you might drag them around in space to represent where the distance can represent the similarity between those documents. It's also been used to predict the success of visual search tasks. So if you've heard of like the Finding Waldo, like Where's Waldo visual search task, then this is the interactions can predict whether someone's going to be successful, and they've also linked particular personality traits to the interactions that people are performing. It's also been used to recover people's reasoning processes about the insights and the data that they find after they've explored and made decisions. And my research is focusing on a slightly different interpretation of those interactions. So I'm interested in making inferences about a person's biases based on the way that they're interacting with the data. So again, that's not a perfect capture of a person's cognitive processes. Interactions are a very lossy way to capture data, but it does give us a trace or a rough approximation about a person's reasoning processes and the biases that may be influencing that. So the ultimate vision of my research is to understand how these visual analytic systems can intervene in real time to help people make better decisions. So let me give you a quick example of that. So it's not uncommon now for people to submit job applications online. So you can imagine that there's a hiring manager who's analyzing the application pool by using some kind of visual analysis system like this. So there might be an interactive scatter plot, table of information about all the candidates down below, filter controls off to the side. And maybe as they're interacting with these candidates and trying to make a decision on who to call in for an interview, the hiring manager may not realize that they focused mostly on male candidates. So we could envision a system that can intelligently detect when there may be implicit gender bias at play, and maybe pop up a recommendation that will suggest that they go look at similarly qualified female candidates. So if systems can intelligently detect when people might be susceptible to biases, then we can design systems that shed light on that and help people to become aware of those biases and hopefully make better informed decisions. So to reach this goal, I'll describe a brief overview of what the rest of my talk is going to look like. So there are 3 high-level phases in my work. So currently, visualization systems support users interacting to explore their data. But as I mentioned, there are many biases that can influence that analysis process. But the term bias is used in many different contexts to refer to entirely different concepts. So the first phase of my work is focusing on defining bias in the context of visual analytics. And once I've contextualized that terminology, I'll turn my attention back to analyzing the way that users are interacting with the data to form an approximation of the biases that they may be susceptible to while they're analyzing data. And using that knowledge about how the user's analysis process might be biased, we can develop mitigation strategies that can guide users back to a less biased analysis process by modifying the visualization interface itself. So again, by creating these interventions that can create real-time awareness about biases, we can hopefully help people make better decisions in the end. So starting with phase 1, defining bias. The question here is, how do we define human bias in the context of visual analytics? And the caveat here is that I'm referring to human bias as opposed to other concepts like algorithmic bias. So I examined the literature on bias in cognitive science and in visual analytics, and tried to categorize the way that the term bias gets used, and tried to think about how each of those perspectives is relevant in visual analytics. So my collaborators and I distilled this down to 4 different perspectives that are potentially overlapping in some ways. So the first perspective is bias as a cognitive processing error. So I alluded to an example earlier in the beginning talking about confirmation bias. So this is really aligned with the classic cognitive science definition of bias, where you think of it as an unconscious error that results from the way that people are using heuristics to make quicker decisions. So in cognitive science, there have been hundreds of types of these biases and heuristics that have been cataloged and studied very heavily. So I'll just zoom into part of this. So there are dozens of errors that result from people having to process too much information. So that includes things like confirmation bias that I mentioned earlier, as well as anchoring bias, which I'll get into a bit more later on. And in visual analytics, this perspective on bias has become really important in the last 3 or 4 years. There are recent papers that have shown that people who are analyzing data with visualizations are susceptible to those same types of biases that have mostly been studied in the cognitive science community thus far. So for example, this paper by Avanthia Damara and colleagues showed that when people are using scatter plots to make decisions about data, they're susceptible to the attraction effect, which essentially means that when there are clusters of points, that influences the way that people make choices, even when those nearby points might be inferior to the one that they ultimately target. So the next perspective is bias as a filter for information. So this is really about perception. So when there's overwhelming information, this perspective on bias really is about how sensory information is prioritized and interpreted. So everyone doesn't experience the same objective version of reality. So next, I have a quick example of this one. You may be familiar with this already. It's about a bias called selective perception. So researchers asked participants to count the number of times that a basketball was passed between the people wearing white shirts. And usually people are able to get that answer correct pretty easily, but due to that selective perception, they don't notice that a man in a gorilla suit walks across the middle of the court. So in visualization, this perspective on perception has really been the focus for some time, going back at least to Gestalt psychology. So this describes the way that we perceive patterns among visual elements. So for example, in the top middle there, we perceive things that have similar visual properties to have similar internal properties as well. And we use these principles in visualization design to really understand how to best leverage human perception and produce optimal designs. The next perspective is bias as a preconception. So we're shaped by our culture, our beliefs, our individual experiences, and by everything that's around us. So this perspective on bias includes prejudices, preconceived notions, and stereotypes that we may carry around with us. So that can include things like gender bias or racial bias, which may be implicit or may be explicit. So this has been studied a lot in the social science community, but it's probably the least formally studied perspective within visualization. So the final perspective is the idea of bias as a model mechanism. So bias often has a really negative connotation. We think of it as this bad thing that needs to be eradicated. But from this perspective, bias is really just an objective measure. So when you have a choice between two options, A and B, how often do you choose one over the other? And in cognitive modeling, you can quantify that decision boundary using a term called bias. So in visual analytics, there have been a couple of papers that have taken this approach to try to quantify something about the analysis process based on the way that people are interacting with the data. And that one on the left is one of my papers that I'll talk about in the next section. So I published these 4 perspectives on bias at a workshop at IEEE Viz. And since then, it's also been published as a book chapter in a book called Cognitive Biases in Visualization. And then in my own work since then, I've used these perspectives a lot and made a lot of progress toward understanding how they're relevant and applied in the context of visualization. And I'll go through these later on as well. But the takeaway message from this phase of the research is that now that I've defined this psychological construct of bias in the context of visual analytics, I can use this going forward to organize and contextualize the work on bias in visualization. So phase 2 of the research is focusing on the question, can visual analytic systems characterize human bias in real time during the analysis process? And the emphasis here is on real time. So in the cognitive science community, there are models for quantifying bias, but usually that only happens after people have made a series of decisions in the context of a laboratory experiment. And in my work, I really want to characterize bias during the analysis process and before a potentially bad decision has been made. So first, I'll describe a bit of the theory and how I developed the metrics, and then I'll show you how I evaluated them later on. So tying this back to the first phase of the research, here I'm adopting the perspective of bias as a model mechanism. And what I mean by that is that I want to derive a set of metrics to objectively quantify or model the user's analysis process without necessarily implying anything about that process being good or bad just yet. So I developed a set of 6 metrics. that can be applied to user interaction sequences to characterize bias in the analysis process. I'm not going to dig into the math here, so I have some more friendly, intuitive descriptions of the metrics to make it a bit more digestible. But if you have questions about the math, I'm happy to answer that. Those 6 metrics are each represented as a number between 0 and 1, where 0 is representing no bias and 1 is representing high bias. And if we look at those numbers over time as users analyzing data and interacting, we can get an idea of how those interactions may have been biased early in the analysis process or potentially mitigated and reduced later on by interacting with additional data. And those rely on comparing interactions that we observe from the user to some notion of unbiased behavior using a Markov model. So the Markov model lets us predict with some probability what the next interaction is that the user will perform given their current interaction. So here there's 2 states in the Markov model, E and A. And each of those states has arrows that are exiting it, representing the probability of transitioning to another state. And the sequence of states that the user enters forms a chain. So the states in my research are made up of tuples of the interaction type. So that could be clicks, hovers, drags, whatever kinds of interactions are supported by the interface, paired with the data point that the user interacted with. So just to give you a quick example of that, here's a scatter plot that has 15 data points in it. And let's say that there are hover and click interactions in that visualization. So in this case, the state space has 2 types of interactions supported, clicks and hovers, 15 data points, so there are 30 possible states in that state space. And we use this model to try to understand how likely a particular sequence of interactions is that the user performs. So we compare, the observed interactions that the user performs to some expected behavior using that Markov model in a variety of statistical tests. So the first example that I'll go through is the data point coverage metric. So this is a ratio of the number of unique data points that the user interacts with compared to the observed number of interactions. So for example, let's take this scatter plot of job candidates. And let's say that there's a hiring manager who is really interested in one candidate, A. It's up in the top left. Point over here too, just so you can keep track of that. So maybe they're particularly interested in that candidate, and they'll keep returning to that same candidate. So I'll animate this in just a second. But for this metric, we keep track of the total number of interactions that the user performed, the number of unique data points they interacted with, and then right above that, I'll visualize what that 0 to 1 metric value is over time. So as the user starts out, the bias metric value is low. And as they interact with new data points, it stays low. But when they start to return to that same data point A again, the value spikes. And then it sort of fluctuates as they interact with new data points, but keep going back again to that same candidate of interest. So another example that I'll go through is the attribute distribution metric. So this is comparing the distribution of the user's interactions with the data to some real underlying distribution in the data set. So let's say, again, that there's a job ad, and it's requesting candidates who have 3 to 5 years of experience. So that's the attribute that I'll focus on. And let's say that you get an application pool that really reflects that distribution. So on the x-axis, there's years of experience, and it peaks at kind of 3 to 5, as you'd expect from the job ad. And the hiring manager is exploring those candidates and interacts with the data according to that purple line. So it's pretty close. They're similar distributions. So the distribution, the attribute distribution bias metric is going to be low. But maybe they start to focus more on candidates with slightly more experience and the curve shifts, or maybe it shifts even more. And this metric is ultimately quantifying what's the biggest difference between those 2 distributions of the data. The observed interactions that the user performed and the underlying distribution of the data. So in this case, the bias metric value is going to be higher. But remember, in this case, I'm still just using bias as an objective measure. This doesn't necessarily mean that the analysis process was bad, right? So it may be the case that the hiring manager realized partway through their analysis that they needed somebody who had a greater level of experience, and they interacted accordingly. So I've given you just a couple of examples, but these metrics were really designed to be part of a more extensible theory, where these concepts of coverage and distribution can be applied to a variety of concepts. So for example, if you have multiple views in a visualization system, you might use these concepts of coverage and distribution to understand how people are applying their attention and using these various parts of the visualization. So the details of this work were published at VAST in 2019, which is part of the Premier Visualization Research Conference. So now I need to make sure that those metrics work. So I conducted a formative study to figure out how to use those metrics in practice and make sure that it tells us something useful about the way that the user is interacting with the data. So referring back again to that first phase of the research, I'm taking the metrics that I formulated from the model mechanism perspective, and now I want to see if I can use that model to identify cognitive processing errors. And specifically, I'm going to look at anchoring bias. So anchoring bias is a tendency to anchor or rely more heavily on initial or anchoring information. So I chose to study this particular type of bias because it's been studied a lot in the cognitive science literature, and it can also be fairly easily manipulated through the experimental conditions. So I recruited 10 people and asked them to categorize 100 basketball players by the position that they play. So to explore the data and categorize those points, I developed an interactive scatterplot visualization system. So this was originally built by one of my lab mates, and then I instrumented it to capture and record all the user's interactions and compute those bias metrics on the back end. So the interactions that the user tends to perform here are clicks, hovers, drags, and so on. So the user will hover on a point in the scatter plot to get statistical information about the basketball player in the top right. And then they can color the point by clicking on it to label it by the position that they play. So in order to induce anchoring bias, the participants were divided into two conditions. So in one of the conditions, I gave people descriptions about the basketball players that was related to their physical size. So this was intended to get them to anchor or rely more heavily on height and weight attributes. So for example, one of the descriptions that I used was that centers are typically the largest players on the team. And in the other condition, the descriptions were based off of the role of those positions on the court. So this was intended to get them to anchor or rely more heavily on other attributes of the data, like steals and rebounds. So for example, one of the descriptions here was that centers are responsible for protecting the basket, resulting in lots of blocks. And the idea is that if we gave people the same set of instructions, there would be some variation in how they interact with the data, but it would be relatively little. When we give people different sets of instructions, their interactive behavior is going to be different in ways that the metrics will be able to pick up on. And the greater the difference in those descriptions, the more different the behavior that we would expect to see. So again, the idea with these two different conditions was that the differences in how they interact with the data would tell us how anchoring bias was manifested in people's interactive behavior. So next, I'll talk you through a couple of the findings. So we plotted those metric values over time for the participants in both of the conditions. And what we expected is that the people who were in the size condition would have a higher bias toward height. And that's what we see in this top chart. So the orange line tends to be higher than the blue one. And that means that the people in the size condition tended to rely more heavily or exhibit more bias toward the height attribute of the data when they were given descriptions about the players based on height and weight. And we saw the same trend again when we looked at the weight attribute. So again, the people who were in the size condition tended to exhibit greater bias toward the weight attribute of the data. And we observed a similar trend for people who, for the attributes that people were anchored on in the other condition as well. But collectively, all of this is suggesting that the metrics are really a promising way to capture differences about users' behavior, and specifically for anchoring bias. So the formative nature of this study really helped us figure out how to implement and take these theoretical metrics into practice. So as I mentioned, those metrics are relying on user interactions. So we need to ensure that we're capturing and encouraging lots of interactions with the data. So for example, that might mean that some information is only made available upon hovering on the data point. So again, the goal here is to encourage users to interact more with the data, but also to do so in a way that can map more directly to their information-seeking behaviors. And while we want lots of interactions for the bias metrics to work, we need to also make sure that they're meaningful and not just noise. So think about the mouse moving across a densely plotted scatter plot. For one intentional interaction, you might accidentally hover on several other points along the way. So we need some heuristics to filter out those noisy interactions. So one that we used for now was just to filter out hover interactions that were below a certain threshold. So we could be more sure that it was intentional and they were actually trying to gather information. Now, this doesn't account for every possible accidental interaction, but it does give a starting point to remove some of the noise from the data. And lastly, the interpretation of the metrics is really important if we really want to integrate and use these bias metrics in a visualization system. So what I found was that that single numerical value by itself wasn't really enough. So it tells the user that they may be exhibiting bias, but it doesn't tell them how necessarily. So we really might be better off by combining this with additional sources of information. So for example, that data point coverage metric that I gave an example for earlier, if that value is high, it says that the user has interacted many times, but potentially hasn't covered that much of the data set. But it doesn't tell them how they may have systematically ignored certain parts of the data. So by providing some additional visualization of what that looks like in the data set, it might be a bit more productive approach. So the details of that work are written in a paper that was published at the conference Interact and then presented back in September. And the takeaway from this part of the research is that now there's a computational set of metrics that can characterize bias with some amount of fidelity just based on the way that the user is interacting with the data. So in phase 3 of the research, this is addressing the question, can the bias metrics be used in visual analytic systems to mitigate bias? So again, referring back to that first phase of the research, I'm taking that perspective again of the bias metrics as an objective or model mechanism, and then this time trying to see if there's some relationship to preconception biases. So in this case, I'm going to look at implicit biases. So implicit bias is describing how our judgment can be unconsciously impacted by certain attitudes or stereotypes that we may have. So that can include beliefs about gender, sexuality, race, and so on. And I want to clarify that this is not the same thing as overt discrimination, right? So it's not intentional. Implicit biases are not intentional and they're not conscious. So despite our best efforts, if we think really hard about it, it doesn't necessarily fix the problem. So to study some of these implicit biases, I chose a recent politically relevant scenario in Georgia. So I asked people to choose a committee of 10 politicians to review public opinion on the heartbeat bill. So that was passed back in May last year, banning abortion in Georgia after 6 weeks. So in this scenario, I would expect to observe some bias toward particular genders in the data set, toward maybe your own political party affiliation, toward particular age groups, and so on. But for the rest of this part, I'm going to just focus on gender bias. So I generated a data set of 100 fictitious politicians. So here's one example. Each politician is described by biographical attributes like their gender, their political party, their occupation, and so on, as well as attributes describing their views on specific policies. So for example, are they opposed to or in favor of things like legalizing medical marijuana or increasing gun control legislation? So the names for each of those politicians was generated based on U.S. Census data, and then the distributions of the ages, occupations, religions, and so on is based off of what's found in the U.S. House of Representatives. So here my collaborators and I developed an interactive visualization tool using D3 and Vega Lite to render the visualizations, and then Python on the back end, again, to try to analyze those interactions and compute the bias metrics. The primary view in this case is an interactive scatter plot. So each dot is representing one politician. And you can arrange those politicians in the scatter plot by changing the x and the y-axis values. And when you hover on a point in that scatter plot, you get details about the politician down below. So if you want to add that politician to the committee of 10 people, you click on that star icon in the top right of that detail view. And you can see the list of the people that you've chosen on the bottom right. And on the left-hand side, there are filters. So if you want to look at just a particular subset of those politicians, you can apply the filters accordingly. And this last part of the interface is especially interesting, so I'm going to break that down a bit more next. So I wanted to show users traces of their interactions with the data to see if that would increase their awareness of what they've interacted with and what biases they might be susceptible to. So I showed that in the interface in a couple of ways. So first, if I just zoom in on that part of the interface, here I'm using gray to represent the underlying data and blue to represent the user's interactions with the data. So this view is going to compare the user's interactions to the underlying data set. And as they interact with the politicians in the scatter plot, those blue bars are going to update and grow in real time based on what data they're interacting with. So let's look at one attribute up at the top. We'll look at party. So in this case, the gray bars show that there are slightly more Republicans in the data set on the right than there are Democrats on the left. But the user's interactions in blue are skewed very heavily toward Democrats. So let's look at another one. So now if we look at age, for numerical attributes, we used these distribution curves. So the gray here is showing that the average age of the politicians is around 58. But the user's interactions in blue are skewed heavily toward interacting with older politicians, so mostly between the ages of 60 and 75. And then down below that, we can see the distribution of those ages broken down into 4 quartiles. So the gray bar on the left is showing that this user hasn't interacted with any politicians below the age of 52. So zooming back out, we also showed the interaction traces in the scatter plot as well. So as the user clicks or hovers on points in the scatter plot, the colors are changing. So those unfilled circles are politicians that haven't been interacted with at all. And the darker the blue, the more the user has interacted with that politician. So, and again, the point of showing that additional view in the data and showing the colors of the points in the scatter plot was to really try to increase people's awareness of what they've interacted with so they can make a more informed decision. So to assess the effectiveness of that, I ran a study. So my collaborators and I recruited 24 people. We randomly divided them into 2 conditions. And then each person completed 2 phases of the study. So in the first phase, I asked participants to select that committee of 10 politicians from the data set of 100 to review the heartbeat bill. Afterwards, I showed them how their interactions compared to the underlying data set in a summative visualization. And then if they wanted to, they had an opportunity to revise the committee that they chose. So participants in the intervention condition were able to see the interaction traces in real time, like in the interface that I showed you earlier. So the colors and the curves would update in real time based on the data that they were interacting with. And the participants in the control condition used a version of the interface that had those interaction traces removed, but it otherwise had the same functionality. So you can see in the top right that additional view is missing, and we're also not coloring the points in the scatter plot based on the user's interactions anymore. So what did we find? So again, my goal was to understand if visualizing these interaction traces, whether in real time or afterward as that summative view, would be able to increase people's awareness of potential implicit social biases. So again, I'm going to focus here on gender bias. So let's look at the ratio of the males in the committee that people chose. So out of the 10 people in the committee, how many of them were men? So I'll compare that after phase 1 along the x-axis, and then again after people had the opportunity to revise in phase 2 on the y-axis. The scale for both of those goes from 0 to 1. So in this case, 0 means that the committee was all women. A ratio of 1 means that the committee was all men, and so on. So I'll show the control condition participants as those purple triangles. So what we observed for those participants is that they tended to actually choose pretty equal numbers of men and women, mostly in the 40 to 60% range in both phases. And the average that we observed was 0.49. Now, remember that in the intervention condition, that visualization that I used really encouraged people to interact proportionally to the underlying data set. So in the data set of politicians, this meant 80% men and 20% women, which was, again, based off of the distribution that we find in the U.S. House of Representatives. And that had a big impact on the way that people chose their committee, right? So the intervention participants, those who saw their interaction traces in real time as they interacted with the data, tended to have a much higher ratio of males in their committee. They tended to choose much closer to that underlying distribution in the data set of 80% men and 20% women. And the average that we found in this case was 0.68, which we found that difference to be statistically significant. But wait, did we just make people more biased, right? So ultimately what this means is that we were able to nudge people to make more proportional choices to the underlying data. But at a higher level, now this, of course, made us question, what does it mean to make balanced or unbiased choices? Because the way that we're nudging people can have some serious implications. So when do we want people to choose proportional to the underlying data versus equal to the underlying data? So for example, let's say we have a population of 20 people and we want to choose a sample of 10. So if the starting population has an equal number of men and women, then in this case, choosing a proportional sample means choosing 5 men and 5 women. And likewise, choosing an equal sample also means choosing 5 men and 5 women. But what if the initial population wasn't 50-50? Instead, maybe it's 70% men and 30% women. So now when we choose a proportional sample, that means choosing 7 men and 3 women. And choosing an equal sample means, again, still choosing 5 men and 5 women in spite of the fact that there's a mismatch with the underlying distribution of the data. So what I found is that we have the power by changing the visualization in relatively subtle ways to nudge and influence the way that people are interacting and the things that they choose. But it's really an open question still when each of these perspectives is the appropriate one to take. So what is the ideal user behavior in a particular scenario? And when we're designing these metrics to characterize bias based on the way people are interacting with the data and designing interventions for the system, we really have to think about what is the ideal user behavior that we want to observe. And that really carries some heavy ethical and moral considerations. So summarizing some of the findings from this study, I found that we're able to nudge participants toward choosing more proportional gender composition in the committees that they chose. But again, now we have this social responsibility where we need to make sure that we're designing interfaces that are encouraging people to make thoughtful choices and that we're not unfairly influencing the way that they interact with the data.
So can you say a little bit more about the task? So I'm just confused about the role of abortion in this. That am I trying to find a committee that agrees with my views or an objective committee? Or
So the prompt for people was to choose a committee of politicians to review public opinion. And for context, this was a highly controversial bill, right? I mean, there were lots of people who loved it, lots of people who hated it. So what we expected in this case is that people would bring their own biases into the interpretation of that task. So people are very likely to choose a committee that they would like to agree with them, right? If I'm a Republican or a Democrat, then I'm likely to stack the committee accordingly to get the results that I would like to observe. So the results of this study are written in a manuscript that's currently under review. But in addition to developing that interaction trace strategy that I just showed you, I also more broadly considered the design of visualizations in general and how we might manipulate them to impact decision-making and mitigate bias. So my collaborators and I came up with 8 dimensions about a visualization that should be considered when designing visualizations that can better support decision-making. So the core parts of the visualization that we can manipulate are the visual representation and the interaction design. So in that last study that I showed you, Remember, we colored the points in the scatter plot and added an additional view in the top right to visualize the interaction traces. So in that case, we modified the visual representation, but didn't adjust the interaction design between the two conditions. There are also other supporting design considerations that really inform and constrain the way that we're able to manipulate the visualization in the interaction design. So one of those is the type of debiasing information that you have. So in the context of my work, that's interaction data. It's everything that we can infer and gather based on the way that the user is interacting with the data. I also considered several things that really might only be manipulated in the context of particular tasks. So for example, the collaborative nature of a decision. So collaboration can be a great way to mitigate bias. You have someone else essentially check your work. They might be able to catch things that you missed or pick up on ways that you might have been biased in the data, but that might be only relevant in some situations. So if I'm making a personal healthcare decision, for example, it may not be appropriate to try to inform people of their biases via collaboration. And then lastly, connecting the user back to the system. I also encourage that the system should support user feedback when possible. So that can help to refine the model of bias that we use based on the way people are interacting with the data. So if you remember the example from the beginning about the hiring manager who's looking at job candidates and there may be some implicit gender bias. So the system gives them a notification that pops up and says, have you considered these female candidates that are similarly qualified? And the hiring manager may accept that recommendation and go look at those female candidates, or they might dismiss the notification. And if they dismiss the notification, we have an opportunity to get some feedback from the user. So we might ask why. And it may be the case that the system is just notifying the user too much and they're getting kind of annoyed and they want to focus on something else. Or it may be the case that there's not implicit gender bias involved. The user's not annoyed by the notification frequency, but they've maybe divided the workload, and they've said that one hiring manager is going to pick the top 5 female candidates to interview, and the other is going to pick the top 5 male candidates to interview, so that they ensure they have an equal representation in their interview circuit. And so by providing that feedback to the system, we can refine that model of bias on the back end so that we can better understand what constitutes user bias. So this design space, along with some examples, was published in a paper last year at IEEE Viz. So the takeaway message from this phase of the research is that now we have a design space to understand how visualizations can be used to improve bias decision making and have some evidence of their efficacy with implicit biases like gender bias in the context of political decision making. So next I want to take a few minutes to talk about other projects that I would be excited to work on next. So a high-level theme of my research agenda deals with human limitations in decision making. So immediate next steps for my research would largely have 2 components. So first, how can we refine the bias detection models? So can we create a more precise characterization of what biased behavior looks like? So I've done some preliminary work toward this goal in a paper that was published, again, last year at IEEE Viz, but there's still a lot that I can do to improve those metrics using and applying them to different visualization techniques and across different decision-making contexts, potentially using different methods for quantifying that bias. And in addition to trying to more precisely measure bias, another next step is to continue to evaluate some of these reflective strategies and how effective they are toward making people aware of what biases they may be susceptible to. So I've only tested the interaction traces that I showed you so far, but there's a whole spectrum of techniques that you could test out, including the example I showed earlier about pop-up recommendations and so on. So I also started this talk with the caveat that I was going to focus on human bias. And as I mentioned, there's an increasing body of work that's been done to understand human biases in visualization. But likewise, there's a growing body of work in areas like bias and fairness in machine learning. And yet there's very little, if any, cross-pollination across those 2 fields, where we're using very similar terminology to refer to concepts that are different in many ways, but also very similar. So I'd like to compare the work that I've done on human bias detection and mitigation and visualization to the work that's been done on fairness and explainability in machine learning, and see what each can learn from the other. So for example, are there parallels between these two fields? Are there techniques that have been used in the context of fairness in machine learning that might be applicable for mitigating human bias in the context of decision-making with visualizations? So lastly, another area that I'd love to dig into deals with an entirely different decision-making context. So how the power of visualization might be applied in the context of misinformation. So this is an increasingly critical issue. There are headlines about high-impact issues like climate change. There's political mudslinging, where every piece of information we don't like we call fake news. And misinformation is having a very real impact, right? We're seeing outbreaks of diseases that have largely been eradicated because people think that vaccines are causing autism. And of course, it's not just isolated to these articles in the deep, dark corners of the web. People are reading and helping spread misinformation through mainstream social media platforms. And there are fact-checking resources that are available, but people are really not seeking out this information. They find things that they agree with, and they share it. So again, there's a body of work that's begun to grapple with a variety of problems in the context of misinformation. So there are social media researchers trying to understand how and why fake news spreads. There are data mining folks trying to automatically detect articles that may contain misinformation, and so on. But given my focus on improving analysis and decision-making, I think there can be some transferability of approaches here, where really the focus of my work has been to promote a more reflective decision-making process. So I suspect that it may be the case a lot of these strategies, these subtle visualization strategies that can promote a more reflective decision-making in the context of visualization might also help make people rethink and become aware of the validity of the news sources that they may be reading and sharing. And it may work well for both purposes. So summarizing some of the work that I've done on bias, I'm really focusing on trying to improve decision-making by quantifying when people might be susceptible to biases based off of the way they're interacting with the data, and figuring out how to design interfaces that can help make people more reflective of that decision-making process and the biases that might be influencing it. And that really has a heavy focus on making implicit aspects of decision-making more explicit and making unconscious behaviors a little bit more conscious. So I highlighted several papers that have dealt with bias. I talked about these during my talk, but there are also several other projects that I've worked on that have enabled me to work on this focus on bias that are all also very related. So, for example, I've worked on a couple of projects that deal with making inferences from user interactions. So sketch interactions and scatter plots, as well as the way that people rank data points, and trying to make inferences about their intents and interest in the data. Also trying to make people aware of what others are working on in the context of a collaborative visualization. The HCI folks will be familiar with heuristic evaluation. So I've also worked with collaborators to develop a heuristic evaluation methodology that's specific to the context of visualization. And worked with folks at Microsoft Research to develop guidance strategies for helping machine learning novices to build better models. And these diverse experiences have really given a broader context to the work that I've done on bias. Before I wrap up, I just want to acknowledge I use the term I a lot throughout this talk, but this was very much a collaborative effort. So I want to thank my collaborators and lab mates, as well as friends who spent a great deal of time and effort contributing and supporting this work by reading papers and editing, debugging studies, and all the rest. And of course, this wouldn't have been possible without the support of various funding agencies as well. So with that, I'll conclude, and I'm happy to take any questions you might have about the work on bias, as well as any of the other projects I mentioned too.
Thanks, Emily. We have a little bit of time for questions. I think you can get the microphone.
Great. Thank you. So I'm curious what the order of magnitude of change you saw from the intervention you had in the part where you were talking about selection of committee, and how that compared to if you partitioned participants into male and female groups and asked them to do the same task, sort of what the order of magnitude of that difference would look like.
Right. So the question was about if we had divided participants into separate male and female groups, would we have observed in the study similar magnitude of differences there? So one of the big limitations of this study was that it was very biased gender sampling. So we had 24 participants in the data, or participate in the study. Of those, 21 were men. So this was very much... There you go. Georgia Tech undergrads. So this was very much a study in how men primarily will interact differently in these conditions. Yeah.
Super interesting and important. At least the decision-making processes you showed in this talk seem to have, almost by design, kind of no right answer, right? Who to interview for a job, who to put on a committee, things like this. I'm wondering if you or others have looked at situations like profit maximization, if you knew like a history of stock prices or something like that, where it's still very difficult for humans to interact with the data and come up with a good decision, but you can imagine different visualizations still lead to different results that could be more objectively measured.
Yeah, absolutely. So I've mostly focused on these more fuzzy contexts where you're right. Ultimately, you choose some facet of the data that you want to focus on or optimize for. So in the context of hiring, there are various measures that you could imagine you want to focus on. So years of experience or other competencies. But there is some ongoing work that I've got with collaborators where we are trying to look at a different decision-making context that does have a ground truth, in collaboration with some folks who are doing some of the machine learning fairness research. So I think one of the common tasks that's used there is a data set about loan approvals, right? Where there is a ground truth in that particular data set about whether people will repay the loan or not. So that's something ongoing. We don't have any results to discuss about that yet, unfortunately. Yeah.
So in the talk, you talked about how to help visualization users to mitigate biases. Do you have any other guidelines for visualization designers to design visualizations that will have less bias?
Yeah, so really the design space that I was discussing a bit earlier was mostly for the context of visualization designers. So when you're building a system and you want to support decision making, you want to encourage a more thoughtful or reflective process. This was really, intended to be kind of a checklist. Have you thought of these different components of the visualization? Yeah. Yes.
So this, you probably get this question all the time, but it feels to me, this ideas that you have in the bias mitigation could obviously be reversed for bias amplification. What are your thoughts on that?
Yeah, we accidentally found that in the study results, right? We were, encouraging people to interact proportionally with the data, and that it turns out that people's natural inclination was already like a pretty good one. They were trying to balance gender and political party, and by encouraging them to interact proportionally to the data, we actually induced a bias. It can absolutely be used for evil purposes. So that's really something I want to focus on going forward as well, is really think through in which situations you want to encourage particular parts or different behaviors in people. Yes.
So in the data that you were showing, the attributes about which one might have bias might not be ones that users would necessarily choose as axes in the visualization. And in the examples, you tended to show them that way. Did you have any sense, did you track the kinds of attributes that people looked at in order to understand whether they were explicitly trying to use them to be fair or not? And if they didn't, did that change their behavior?
Yeah, so we did track their interactions with the axes as one measure of what was explicit versus implicit. And we also asked people afterward in the survey, what attributes of the data were you relying on? And what do you hope the outcome of the committee would be, and those sorts of things. So we could try to tease apart what was implicit versus explicit. It turns out it's still very difficult to tease apart implicit and explicit. People were thinking about these things, but they still ended up choosing very biased samples in spite of their attempt to explicitly balance something. Ongoing work to hopefully try to separate out what's implicit versus explicit a little bit better. It's still very fuzzy.
All right, I have one more question, actually. I was wondering, so you talked a lot about detecting biases from the interactions, but what if, and I think that kind of is in line with Curtis's question a little bit, what if somebody's goals are to actually select a sample, or to select data points that are biased, but that's okay because it's in line with that somebody's goal? What would you recommend in terms of, can we maybe test for somebody's goals in advance? Would we ask for it? Are there maybe ways to automatically interrogate?
Yeah, so the question is about, again, explicit decision-making criteria versus, implicit biases. A lot of the work that I mentioned here about supporting user feedback is kind of the key that I envisioned to being able to help refine the model. The model of bias is, again, just supposed to be an objective measure. We don't have any value applied to whether that's good or bad apart from what we impart on it ourselves. So bias toward higher level of experience in your job candidates is bias from a subjective perspective, but it's not necessarily a bad one. Whereas bias toward gender is something that most folks would agree is probably one that we want to be a little more careful to protect. So I really think the key comes down to this closing the loop and supporting user feedback a bit better. So if the system is giving you a notification about a particular type of bias that you find to be an explicit decision-making criteria, we can refine the model of bias on the back end and not keep annoying people with those suggestions. Or in the context of if it's like a hiring system, then probably beforehand you can specify which attributes are the ones that should be protected and cared about, so that it's not from the beginning not unnecessarily notifying you about things that are explicit.